Good evening, and welcome to the second of three videos on the linear regression. What we're going to start with today is what's known as the standard error of the estimate. And what this is essentially the amount of variance or the standard error around the of the y-scores around a particular value of x. So you may recall that there may be multiple values of y for each value of x, right? You got an x here, you got an x here, you got an x here, and there's bunches of values of y. And so that gives you, when you calculate the linear regression, something that looks like this. Well, there's a range now of values here and here, all right, and so on. And so this is what we're trying to calculate, or what we're trying to estimate. Smooth. That's what we're trying to estimate when we talk about the standard error of the estimate. So what that means is that, let me get rid of that. What we're trying to do is to figure out what the average error is in our values of y prime. All right, and that's what's known as the standard error of the estimate. All right, so the standard error of the estimate is as close as we will come to computing the average error in our predicted y's. All right, the loops that I showed you a little bit earlier. And the way that we calculate this is we calculate the value y prime, right, the standard error of the estimate, as equal to the standard error times the square root of 1 minus r squared, where r represents the correlation coefficient. All right, so this is the calculation that we're going to use. Now, in the third video, we'll do some of these calculations so you can see actually how they're done and what variables to use as we do the calculations. But for now, just make sure that you've got this formula in your bag of tricks. All right. At this point, you should have a nice piece of white paper or notebook paper, whatever it is. All right. And you should be making lists of all of the various formulas that you need for doing this kind of work. All right. Given that your final exam is coming up on Thursday, this is something that you really should start making lists of. Right. Start from chapter 1 all the way through the end of chapter 8. All right. So this is the formula for the standard error of the estimate. So that's all fine and good. Calculating it is one thing, but then knowing what it means is something quite different. So how do we actually interpret the standard error of the estimate? What is it? What does it actually mean once we've got that number calculated? All right. Well, before we do that, there's a couple of things that we need to talk about. All right. The first is a set of assumptions, and there are multiple assumptions, not just one. But about linear regressions, all right? And so the first assumption of linear regressions is what we call homoscedasticity, all right? I always bumble over that word, but homoscedasticity, all right? When the data are homoscedastic, what that means is that the standard error of the estimate, S sub y, or S sub y prime, accurately describes the average error. All right. Now, what that really means is that the average error is pretty much the same all the way up the regression line. All right. In other words, the data are spread out a certain amount. For every value of x, they're spread out the same amount. All right. And so that's what we mean when we say homoscedasticity. Say that 10 times fast, I dare you. Now, so when the data are homoscedastic, that means that the standard error of the estimate is fairly constant. No matter what value of x you're dealing with, you've got that same level of error all throughout the line, no matter where on the regression line you actually look. So what does that look like? Well, here is a wonderful little graph that shows a data set that is homoscedastic. All right, we've got widget test scores on the x-axis versus the widget making scores on the y-axis. And you can see that the average error is pretty consistent no matter what value for the y's it's pretty consistent for every value of x. There's 4 or 5 data points or y values for each value of x, and the data is spread out to a pretty even degree. All right, and so this illustration shows a homoscedastic data set, and this occurs when the y scores are spread out to the same degree at every value of x. Now, you may say to yourself, oh, yeah, well, that should happen all the time. But that's not true, because there are also great examples of heteroscedastic data. And this is an example here. Now, we've used the same x and y axes in this particular graph. So we've got the widget test scores on the x-axis and the widget making scores on the y-axis. But here, the data is heteroscedastic. For the very low values of x, there's very little variability in the widget making scores. But when the widget test scores get large, there's a great deal of variability. You can see that there's a much bigger range when the x scores are large than when the x scores are small. All right. And so this is what we would refer to as a heteroscedastic data set. And this occurs obviously then when the spread in the y values is not the same throughout the relationship. All right. Obviously, it's much different for big values of x here as opposed to little values of x. Now, the second assumption of linear regression that we have to make in order to get this to work, all right, is that the y scores at each x form an approximately normal distribution. In other words, most of them fall right around the mean, and fewer fall of the y scores fall at greater distances from the mean value of y. Now, interestingly enough, when we talk about the normal distribution here, we're not going to talk about the normal distribution, because we're used to seeing it drawn like this, right? And we're talking about a normal distribution of the x scores, right? Of the y scores related to x. Now, we're going to talk about each x score having I don't know if I can actually draw this. Maybe. All right, a normal distribution that looks something like this. All right, and so the regression line, I missed. Damn it. Sorry. The regression line is going to look something like that. All right, and there would be the R line, the regression line. And so in this case, the normal distributions are going to be kind of turned on their sides, because we're talking about the normal distribution of the y scores rather than of the x's. All right, and so this is a much prettier diagram than the one I was trying to draw in the previous slide. Here we've got widget test scores of 1, 2, 3, and 4 respectively, and then the widget making scores, all right, in widgets per hour. And you can see that for widget test score 1, the average widgets per hour is 3, all right? But there's a few that are much smaller and a few that are much larger. For the widget test score of 2, the average widgets per hour is about 4, but there's a few that are lower and a few that are higher. For the widget test scores of 3, the average is, it looks to me like about 6-ish, and for widget scores of 4, or test scores of 4, the widgets per hour is around 7-ish. All right, but you can see that each of these 4 widget test scores has a distribution of y scores that roughly approximates a normal distribution. Okay, so when we're talking about these normal distributions, we assume that we have a very good idea of whether or not the relationship is very strong. All right, is the data spread out about that mean value of y, or is it all bunched together at that mean value of y? And if the values of y are all bunched very close together, that represents a very strong relationship. If the values of y at any given value of x are all spread out, and so there's a big stretch in the normal distribution, then that indicates a very weak relationship here. Now, do you have to draw a little normal distribution at each point? Absolutely not. All right. You'll be able to tell just by looking at the scatter plot whether the data is bunched together or all spread out. Okay. Now, mathematically, talking about the strength of a relationship, as the strength of the relationship increases, the actual y scores are closer to their corresponding y prime scores. Remember, the y prime score is the average value of y at a given value of x, all right? Or the predicted value of y at a given value of x. So if the relationship is very small, I'm sorry, we start that sentence again. If the relationship is very strong, that means that the values of y are squished together. And so the differences between y and y prime are going to be small, and therefore the standard error of the estimate is also going to be much smaller. All right, that indicates a strong relationship. All right, so when the y scores are bunched together, the differences between y and y prime are going to be small, and therefore the standard error of the estimate is going to be small. All right, and that indicates a strong data set. On the other hand, if those y scores are spread out all over God's creation, then the differences between each value of y and the y prime value are going to be much larger, and that's going to give us a much greater standard error of the estimate, which means that we have a much weaker relationship between the x values and the y values. So this indicates a very strong relationship. You can see that in this particular data set, we've got a correlation coefficient very close to -1. And in this case, we've evenly split the difference between the values above the average y-score and the values below the average y-score, right? Notice, come on now. Notice that there are 2 above and 2 below, 2 above and 2 below, and so on all the way down. All right. And so what that means is that we are very evenly splitting the difference in the y values. Not to mention, all of these y values are very close to that average value of y, the y prime value at each value of x. All right. So this indicates a very strong relationship. And of course, we would expect that because there's a correlation coefficient of almost -1, or at least closer to -1. Now, on the other hand, a weak relationship is indicated by something like this. Now here, all right, you've got, we're kind of splitting the difference between most of these values of y, right? Here we've got what, 5 on the top and 5 on the bottom. Here we've got 6 on the bottom and 5 on the top. So they're still pretty close. So this is here, but notice that the R value is much closer to 0. So there's not a very strong correlation here. And if you look at the data, like this value and this value are pretty far away from the value of y prime, right? Y prime would be right here, all right? And so the data is much, much more spread out at each value of x, and that indicates a very weak relationship here. Okay. All right. Now, the next thing that we have to do is compute what we call the proportion of variance accounted for. All right. So what we're taking into account now is how much of the variance has already been.
It's 8 o'clock.
Well, thank you, Jesus. How much of the variance has already been plugged into our calculations? So the proportion of variance accounted for is the proportional improvement in accuracy when using the relationship with x to predict y compared to using the average y to predict y. Okay, so in other words, when we use the relationship, and by that I mean y prime equals b times x plus a. That's the relationship we're talking about here, all right? Rather than using the average value of y to predict y at a certain value of x, all right? So these are the two different ways that we can look at variance, all right? If we use the relationship, then we're talking about the proportion of variance accounted for. All right, if we use the average value of y, then we talk about the proportion of variance that is not accounted for. All right, so let's start with the accounted for business. All right, so in this calculation, we're actually already taking into account the y prime value. So y prime is going to equal the slope times the value of x plus the y-intercept. Now, so when we do not use the relationship, we use the overall mean of the y scores, all right, which is the average y, as everyone's predicted value of y. Now, when we do this, the error here is the difference between the actual y scores and the average y we predict that they get, all right? So in other words, y minus the average y. And so when we do not use the relationship to predict the scores, our error is going to be the variance here, okay, s squared, okay? So when we do not use the relationship, our error is going to be s squared, okay, or the variance. Now, on the other hand, when we do use the relationship, we use the corresponding value of y prime as determined by the linear regression equation as our predicted value. Now, the error here is the difference between the actual y scores and the y prime that we predict they get. So it's y minus y prime. And this is a much closer relationship. Here, the standard error is s squared of y prime, not of the average value of y, like here. All right. And so this is a much more accurate representation because it includes the variance that we already account for in our equation. All right. So we're going to look at one data set and we're going to look at the linear regression line calculated two different ways. Now, so we've got the assembler test scores and the number of phones that they can assemble per hour. And the average for each assembler, for all of the assemblers rather, is 4. Okay. Now, notice that assembler number 1 never ever got 4 phones put together in an hour. All right. Assembler number 2 did it once. Assembler number 3 did it twice. Assembler number 4 did it 3 times. And assembler number 5 did it 3 times. But the average number of phones per hour of all 5 of these workers is 4, even though assembler number 5 is putting together up to 7 phones in an hour, and assembler number 1 is the highest number of phones he produces is 3. All right. So in this case, we always use the value of the average y to predict the y values. Now, on the other hand, using a relationship, the relationship, the linear regression relationship, we use y prime to predict the y values. Note the improvement in predicted values. All right. In this case, notice that the data is much closer to the linear regression line. All right. All of it falls within a very small distance on the y-axis. All right. If you go back to the previous one, notice, I mean, we're talking about a big gap here and a big gap here. All right. And so when we do use the linear regression relationship, we actually end up with a much more accurate prediction of the standard error for each value of x. Excuse me. Okay. And of course, this is a much better representation of the relationship that exists here. Okay. So to actually compute the proportion of variance accounted for, we have to calculate r squared, which is the square of the Pearson correlation coefficient. All right. So we calculate the Pearson correlation coefficient, and then square it. And then that's the first step in calculating the proportion of the variance accounted for. Now, for when we don't use the regression line, the proportion of variance not accounted for is not r squared, but rather 1 minus r squared. All right, and so it's a very different number, a very different calculation. So the computational formula for the proportion of variance in y that is not accounted for by a linear relationship with x is 1 minus r squared. Okay. All right. So, my friends, that actually is going to be the end of video number 2 for chapter 8. And I hope you learned something.